anti-area volume, which is 1/4 and 1/4. And then you got 1/2 symmetrical volume. So you got 1/2, and then you got 2/4. Well, you got 1/4 and 1/4, which is 2/4, which is us. And then what supports us is the other half of the volume, which is actually all of the volume. And that's where the 1/3 pops up. And you just don't, how is 1/3 popping up when we're doing fourths? These physicists know what I'm talking about, and y'all will too shortly. Here we go.
The Planck constant defines a new source of quantum uncertainty that you can't ever physics away. And we hit that uncertainty at the Planck length. Let's continue our Gedanken experiment. Now adding two key ideas from Einstein. First, that mass and energy are equivalent as expressed by the most famous equation ever, E = mc². And second, that mass and energy warp the fabric of space-time. So, back to Heisenberg's microscope. Let's say we're trying to measure our distance with perfect precision.
Okay.
And who cares about momentum? We keep decreasing the wavelength of our measuring photon, ultraviolet, X-ray, gamma ray, which also increases the photon's energy and momentum. As we crank up the energy even further, we start to notice something. The photon is starting to produce an observable gravitational field.
Boom! Do you see what I'm saying? Can you hear what I'm thinking? If light is massless, how can it have gravity, produce a gravitational field? Because it is mass. We are light. We are fields. You have to keep the iteration of scale, frequency, and summation has to keep folding that space, folding that space, folding that space, because we're in a finite length across infinite scale. So this finite length that's only growing in, how can a finite length grow? Same way 360 degrees grows. Same way pi grows. Grows in scale. That's why things look, that's why when you look at something far away, it seems to go into itself. All the space around. When you look at one object that's a long distance away, it looks small. But when you look at out, everything looks like a bubble. You're in a bubble. It's because what you're looking at far away is radiating to you. And you're accepting it through a negative curvature. I mean, well, it's a negative curvature to whatever's the light's reflecting back off of. It's positive curvature to you because is that positive or negative? Let's see. Well, it's you flip it, it's the same way. But at any rate, positive curvature is out. Negative curvature is in. So we're inside of our eyeballs, but everything outside of them is coming toward a positive curvature, but we're in here. Looking out of a negative curvature to us, to the See, the mechanized field is a negative is a negative curvature. And what the light's bouncing off of from that direction, it's a negative curvature. But for us, it's a positive. Is it? Let's see. Let's make a lens. Yeah, so you got your fisheye lens, and it bubbles everything and pulls everything in to a more. Oh, I'm getting lost. But y'all know what I'm talking about. Okay. See, I'll go off on a tangent. I gotta keep myself focused.
Even though photons are...
See, because relative, am I new? Yeah, kind of, sort of. I didn't really, yeah. Okay, I'm babbling now because I'm having fun. Okay, here we go.
Massless. If enclosed in a system, a photon creates what we call effective mass, according to Einstein's equation. The resulting gravitational field changes the distance to the object, adding a new uncertainty, distance. Okay.
Why does it change the gravity? Because it's a negative curvature. And why is that curvature negative? When it's really not a curvature at all, it's an amount of space that has been folded to the point it's lensing. It is, and what it's lensing is expansion. That's what gravity is. It's the lensing potential of expansion. Well, the gravity focuses expansion. Focuses it inward to a point smaller than the previous expansion. And it's just space folded and folded and folded and folded and folded until you got this thick goo that expansion has to lens through, has to get through. And it can't get through it faster. Expansion can't get through a block of wood faster than it can get through a sheet of paper. Let's say you want to talk topological and flat space curvatures. Let's use a sheet of paper so everybody can start relating. It's a flat sheet of paper. That's space. There ain't nothing on it because it's space. Now you got a flat sheet of paper with a block on this side and a block on that side, on the underside of the paper, and the paper's running through it. Now all of that's the same space. Now let's utilize fire to expand this space. I'm going to expand this sheet of paper over here to a cloud of carbon. So it's going to expand way bigger than what it used to be. And so the expansion will be just, I'm burning up the paper, okay, from the center point. So the burning will be like the opening of Bonanza, credit Bonanza, with Cartwrights and whatnot, if you're old enough. But at any rate, just like that, how it radiated outward, okay, that's what I'm going to use for expansion. I set fire to the middle of the paper. And it's expanding. Now set fire to the middle of the block with the paper on the inside. Eventually, it'll burn, expand. But it's not going to expand